Hi everyone. Today I will discuss some of the research conducted during my PhD. So past descriptions and even modern scientific investigations on the impacts of volcanic events tend to focus on air quality and the effects of particulate matter on the respiratory system, probably because these are often considered to be among the most visible, widespread, and damaging forces released during eruptions. The current research rather aimed to consider a wide range of skeletal changes potentially associated with exposure to volcanic pollutants, such as mercury and fluoride from the atmosphere, food, and water. Though asphyxiation is the most common cause of death resulting from volcanic eruptions, the aim of this project shifted to consider volcanic impacts on human health more broadly. Additionally, other research on Iceland and sites throughout the North Atlantic have often connected respiratory disease to indoor fires and smoke inhalation, making such skeletal changes difficult or impossible to differentiate from those potentially arising from volcanic emissions. Thus, the osteological investigation aimed to consider bone changes that were indicative of health stress, metabolic or nutritional deficiency, and toxic exposure to volcanic emissions capable both of accumulating in bone and causing skeletal change or reaction. How did the environment affect human health, and how did the population respond to volcanic events? Volcanic eruptions can negatively impact human and animal health, as well as cause local or global climate change and pollution by releasing numerous gases and particulate matter. Active volcanic systems release emissions both during eruptions and between them, known as passive degassing. Aside from respiratory conditions and fluoride poisoning, volcanic eruptions also directly cause other health conditions, such as carbon dioxide poisoning and crop, groundwater, and residential contamination, which occurred, for example, with the Mount Hekla eruptions of 1947 and 1970. In addition to chronic and acute diseases, smoke, tephra, ash, and silica inhalation following eruptions have been linked to neoplastic diseases or cancer. According to historical records, nearly all 23 historical eruptions of Mount Hekla produced toxic fallouts, many of which contaminated grazing lands and water and food sources that would have caused the mass mortality of livestock and potentially people. Today, people and livestock may be exposed to fluoride and other heavy metals in Iceland if they reside too close to aluminium smelting factories, for example. Other sources of modern exposure include fluoride toothpaste and mouthwashes, broken thermometers and light bulbs, damaged batteries and old infrastructure, and even paint. The descriptions presented here cover skeletal pathologies recorded in this study from individuals from 7 Icelandic archaeological sites. Numerous bone changes and features were recorded because of the multifactorial etiology of skeletal fluorosis and numerous differential diagnoses which share the same bone changes. This includes various conditions that are not connected to environmental origins at all, such as Treponemal Disease, also known as syphilis, and Hydatid Cyst. These are relevant to this study due to the historical use of mercury as a medical treatment for these conditions. In fact, Dr. Jón Hjaltelín, the Director General of Public Health in 1845, reported the recovery of patients of both of these conditions through mercurial treatments. Paget's disease and oral facial clefts are described here because individuals featuring these conditions were identified and provided unique and outlying results likely correlated with their pathologies. Although not found in high frequency in this study, rickets and osteomalacia are described here because these conditions were thought to be common in historical Iceland and in light of their connections with heavy metal toxicity and skeletal fluorosis. Caries, calculus, and periodontal disease because of their relationship and interactions with each other and with fluoride exposure. On the top photo, we can see a sheep bone that has undergone extensive skeletal change due to fluoride poisoning resulting from the volcanic fallout of an eruption of Mount Hekla in 1845. During that eruption, large amounts of fine ash spread to the Faroes, Orkney, and Shetland Islands, and lava flows spread to the west and northwest of Iceland. Most importantly, that fine dark ash spread over parts of Iceland, blanketing pasturing regions, which led to the mass mortality of livestock from fluoride poisoning for up to 2 years after the eruption. Thus, the extent of skeletal change seen on this bone likely occurred due to the animal's chronic exposure and ingestion of fluorine over a long period of time. Unfortunately, this bone was exported to Germany, and in the 19th century, its whereabouts became unknown, and thus the fluoride content in it cannot be tested. The image below shows an example of dental fluorosis known as öskutenner, or ash teeth, in a horse following the 1970 eruption of Hekla. From the 7 sites that were included in this research, osteological and paleopathological analysis was undertaken on a total of 186 adults, or those over the 17 years of age. The 10th to 12th centuries are represented by skeletal assemblages from Skeletal, which believed to have been in use at least until after the AD 1104 eruption of Mount Hekla. The 13th to 16th centuries are represented by 2 sites, the first being Hydatid, which had a cemetery in use until 1563 and included a group of local individuals. The second site was Skeletal, a medieval hospital that began its operation just 16 years after the severe eruption of the volcanic system in 1477. Finally, the 17th to 19th centuries are represented by the assemblages from Reykjavik, Vede, Bessastaðir, and Reykholt. On the map, which I've just gone past, on the map shown here, you can see both the site locations and volcanic systems around the country. The aim of the skeletal analysis, as previously mentioned, was to examine overall health and the possible antemortem exposure to various elements, such as fluorine, which is known to cause characteristic but diffuse skeletal changes. While the other measured elements all interact with the skeleton, none of them regularly cause bone changes that can be directly correlated with toxicity. Standard anthropological methods were used to estimate age, sex, stature, and pathological conditions. Radiography, microscopy, and specialized methods were used when necessary. As you can see on the table, a lot of the indications of metal or fluorine poisoning are non-specific. For example, a traumatic bone fracture can be an indication of fluorosis in the sense that the bone becomes more fragile and brittle after high dose or chronic exposure. But this can also occur with any considerable force, regardless of bone health. Thus, identifying fluorosis and metal toxicities as well in skeletal remains depends on the concurrence of multiple bone change indicators in addition to elemental chemical measurements on the bones themselves. This brings us to the archaeometric aspect of the analysis, which included 50 individuals from 2 sites, being Skeletal and Skeletal. They were sampled for the purpose of stable isotope analysis of carbon, nitrogen, and sulfur, and bone element concentrations of mercury, lead, cadmium, and arsenic. While most of these samples were selected from the adult individuals that were osteologically analyzed, 6 non-adults were also sampled. Trace element analysis was undertaken on dental enamel for 8 elements on a total of 31 of the same people. 22 samples of soil from both sites and 25 animal bones from Skeletal were analyzed alongside human bone samples to examine natural background levels of various elements in the local environment and to control for concerns over diagenetic enrichment. This was also done to investigate differences in exposure between livestock, wild animals, and the human population. Otherwise, extensive isotope analyses on human and animal bones were conducted, but are not discussed here today. Samples were not selected from the 17th to 19th century sites due to the funding limitations, but more so because of difficulties with controlling industry-related variables that notably increased during this period. For example, mercury was used in the production of hats and other textiles. Tobacco use increased, thereby increasing cadmium exposure, and lead or lead-glazed goods became more widely available. However, it would be interesting to investigate toxic exposure in individuals from this period, particularly in comparison with other skeletal populations in Scandinavia and elsewhere in the North Atlantic. Overall, the observed skeletal markers increased with age. This was to be expected considering that many of the recorded pathologies are directly associated with increasing age. There were low rates of vertebral ankylosis and other joint ankylosis. Nearly half of the individuals displayed at least one antemortem fracture, with males and people aged 36 and over most affected across time. Periosteal new bone formation was seen in over half of the analyzed individuals. 72% of them had vertebral joint degeneration and 46 had non-spinal joint degeneration of at least one joint surface. As can be seen on the table, the remaining rates of bone changes in fluoride bone concentrations are noticeably lower in the Icelandic assemblages than they were at Herculaneum, one of the few or only archaeological skeletal assemblages available worldwide with individuals known to have been exposed to a volcanic environment and an eruption which occurred at Pompeii. Fractures, enthesial changes, and interosseous calcifications were higher in all time periods among males and older adults, perhaps because of their strong correlations with gendered behavior, increasing age, and sexual dimorphism. Across all sites and ages, under 41% of individuals showed indicators on at least one bone of mineralization of the enthesial or interosseous attachment sites. Meanwhile, at Herculaneum, 92% of all people of all ages had clear evidence of calcifying changes on at least one bone, but previous studies have all shown a strong correlation to increasing age over activity patterns or pathology. It is interesting to note that fractures and degenerative joint disease were the only conditions that had higher prevalence rates in Iceland than at Herculaneum. The Icelandic fracture rate is probably connected with the local topography and historical occupations, and the joint disease likely due to a combination of genetic and occupational factors. The image on top shows bones with irregular surfaces and morphology, including bone expansion of the shafts. While fluorosis can cause such changes, the radiograph shows aggressive lesions under the cortical surface, indicating rather infectious disease such as syphilis. The bottom photos show a tibia and fibula with healed fractures and a skull with a single tooth. The tooth is fixed within the skull due to the abnormal size of the root, a condition called hypercementosis that can occur due to fluoride exposure. The results showed significantly higher prevalence of changes to the interosseous crest of the lower leg in females, while males had a significantly higher prevalence of interosseous crest changes on the lower arm. The image in the middle shows an example of bone formation at that crest. In light of such results, it is interesting to note that even if distinct gendered roles were in place at the time, women still participated in equally strenuous work, such as farm work, fishing, and textile production. Bone fractures, like shown on the bottom row, can easily occur from such activities, which might also increase the extent of other pathologies like osteoarthritis, which can be seen on the left side. However, as previously mentioned, though enthesial change studies often interpret sexually dimorphic differences as the effect of gender divisions of labor, they in fact predominantly reflect intrinsic sexual dimorphism or biological factors rather than cultural or population-related differences. For clarity, enthesial changes are markers of soft tissue attachments like muscles, tendons, and ligaments that appear on the bone. Metabolic conditions like rickets or osteomalacia caused by vitamin D deficiency are important predisposing factors for skeletal fluorosis. It has often been thought that the vitamin D deficiency was common in Iceland, but the prevalence rates from Iceland described here might be lower than expected because of the long period of sunlight during the summer months and the historic importance of fish and other vitamin D rich foodstuff like milk, cheese, skyr, and forage mushrooms and Icelandic moss in the diet. Overall, 7% had rickets and 3% of them had osteomalacia. While at Herculaneum, for comparison, around 8% of the individuals that had fluorosis also had osteomalacia. However, these conditions are relatively rare in the skeletal record generally, partly because they are difficult to accurately diagnose. Earlier studies have indicated a notably high dental wear rate, probably resulting from parafunctional behaviors like fishing and weaving woolen fabrics, such as vadmal, using the teeth, and local past diets of tough, gritty foods and acidic drinks and dairy products. Carious lesions, on the other hand, have a really low prevalence, which is probably related to the high rate of calculus, heavy attrition caused by the past diet, which was tough, high in protein, and low in flour, grains, and sugar until the 20th century. Additionally, periodontal disease was observed in almost 2/3 of individuals, a condition that often shows increased rates in assemblages with high rates of calculus. This is probably because the plaque concretions chronically press into the gingiva or gums, as well as entrap bacteria, foodstuff, and other particles or fragments. The childhood disease burden of dental fluorosis, though, was low overall. Dental chipping, which may relate to poor enamel mineralization, such as that caused by fluorosis, was present in just 7% of teeth, though in this research it is likely to be associated primarily with diet rather than mineralization. Linear enamel hypoplasia may occur due to childhood fluoride exposure and was the most common enamel defect observed in this research. However, enamel hypoplasia normally correlates with periods of health stress, disease, or periods of malnutrition during childhood. Enamel hypomineralization was only just slightly higher than normally reported in healthy modern teeth, so about 5% of teeth. At Herculaneum, for comparison, all of the prevalence rates were notably higher. From Skeletal, 39% of individuals had increased bone lead concentrations. Though bone is highly susceptible to the postmortem uptake of lead, if diagenesis is not at play, it is nevertheless interesting to note that 57% of those individuals with elevated bone lead concentrations also had elevated dental enamel concentrations, which could imply that these people were exposed to lead both during childhood and throughout life or close to the time of death. Exposure to lead at Skeletal was probably lower because less trade or commerce occurred there or during that time period compared with at Skeletal, which was occupied later and was a center of commerce. At Skeletal, due to the monastic functions and its role in trade, the use of materials such as lead for structures and objects was probably far more common and accessible than at the earlier farm site of Skeletal. From Skeletal, increased mercury concentrations were found in 11 individuals, all of which showed bone markers indicative of either hydatid, treponemal, or some other type of non-specific infectious disease. Overall, the mercury concentrations determined from Skeletal were all elevated and are statistically significantly higher than those from Skeletal, not only between sites, but also across age and sex categories. Elevated concentrations of mercury found in the skeletal population from Skeletal could have arisen from several points of possible exposure, such as from medical use or through pigments like vermilion that were featured in scholarly writing, which was important at the monastery. While mercury was used as a treatment for skin conditions in Europe during the time period that Skeletal was inhabited, it was not commonplace until around the time that syphilis began to plague Western continental Europe in the late 15th century. Marine mercury contamination rose fivefold in the 1800s and tenfold during the 1900s. Therefore, prior to the 19th century, marine animals had far lower levels of mercury pollution than in the present. Thus, diet was not likely a major source of exposure to mercury in medieval Iceland, the way that it could be in some regions now. Additionally, the isotopic results of this research showed that marine protein was unimportant to the diet at Skeletal, whereas the opposite was the case at Skeletal. As volcanoes almost constantly release emissions, known as passive degassing, and eruption events may persist for months or even years, exposure could have happened during eruptions or via residential proximity so close to the volcano. The source of elemental mercury, cinnabar ore, is not found in Iceland, and thus any form of it that was used here had to be purchased from abroad. Mercurial medicine was normally provided through salves spread upon the skin, as well as via fumigation, which required that the patient enter a chamber or closed room where mercury could become vaporized through heating and thus inhaled. So in the X-ray here, it shows the lungs after mercury inhalation. And on the left, we can see a photo of the eruption in the Westman Islands in 1973, which caused significant mercury pollution. Today, for example, populations of birds in the North Atlantic are in decline. While no single contaminant is solely responsible, the combination of numerous natural and anthropogenic contaminants originating especially within the last 200 to 300 years pose a serious risk to marine wildlife, particularly when considered along with the simultaneous occurrence of environmental and habitat change and food shortage. That being said, mercury levels alone in the North Atlantic marine bird species, such as the Arctic tern, are so high that their reproductive success is likely to be affected. At Skeletal, bone fluoride concentrations were significantly higher than at Skeletal, even across sex and age categories. While no concentrations were indicative of clinical fluorosis, 14% of those from Skeletal were consistent with the preclinical phase. Meanwhile, just 2 out of 14 individuals from Skeletal presented with elevated concentrations. At Herculaneum, for comparison, the fluoride bone concentrations were far higher and clearly indicated widespread fluorosis correlated with increasing age, as osteofluorosis often is. In this study, all except 2 individuals with elevated concentrations were categorized as younger adults, possibly suggesting the occurrence of increased exposure from volcanic emissions beyond normal age-related fluoride accumulation that's acquired in uncontaminated drinking water. At Skeletal, the mean bone fluoride concentration was actually lower than first expected, especially considering its close proximity to Mount Hecla, which is a known heavy fluoride and mercury emitter. The highest fluoride concentrations were, though, predominantly observed in those who also had the highest mercury levels and skeletal changes potentially associated with fluorosis. It may be that the individuals had exposure to toxic emissions during the volcanic eruption, especially since some of them post-date the eruption, but others were perhaps only exposed to passive emissions from the surrounding area. Moreover, 14 individuals had robust enthesial changes, which could potentially be correlated with mild osteofluorosis. On the top right, there is an example of Treponemal disease, or syphilis, with severe destructive processes occurring on the skull and the shaft of the tibia. While metal or fluoride toxicity do not cause these changes, this individual had elevated mercury bone content, indicating that they were potentially provided with mercurial medicine during life. Mercury was one of the first, most common and long-lasting chemotherapies used in the past and only fell out of use upon the discovery of antibiotics. On the left is an example of a large Hydatid cyst, also known as syphilis, which is a parasitic infection that is transmitted through a life cycle involving sheep and dogs. As mentioned earlier, Hydatid disease was also treated with mercury in the past, and this individual showed above elevated bone mercury levels as well. On the bottom right, there are two examples of cleft palate. The one furthest to the right shows a congenital example, while the one on the left shows an active bone destruction process, perhaps from infectious disease. The individual with the congenital cleft palate showed no evidence of elevated metal or fluorine in bone, but they faced dietary restrictions, which was demonstrated by him being the only individual at Skeletal to not eat large quantities of fish, with isotope results plotting him within the range of a typical modern vegan. The other individual with destructive lesions on the palate had elevated mercury concentrations, perhaps providing secondary evidence that this person was afflicted with syphilis. Lastly, the radiograph depicts an older male individual found at Skeletal with Paget's disease. This condition is rare in the skeletal record, and almost all cases of it have been found only in the UK. It is interesting in the context of exploring fluorosis because the condition causes some similar bone changes, particularly the expansion and thickening of bone. The cranial bones are nearly twice as thick as those seen in the average person. You can see the lines, for example, of where the original bones were and where the new bone formed upon it due to the condition. Despite Iceland being a rural country well into the modern period, the general health and living conditions do not appear to have been vastly different from any of the neighboring countries. Human groups probably fled from certain regions that were especially affected by volcanic fallout, and unlike the livestock, they probably managed to avoid contaminated drinking water when possible. Therefore, volcanic dangers were not well hidden, especially when it was possible to move away from the ashfall and visible fires of the eruptions. These dangers were probably only concealed during passive periods when natural degassing still posed health risks to those living within close proximity. Although these events dramatically impacted the living conditions and habitability of areas subject to volcanic fallout, sometimes resulting in site abandonment, the actual health burden of skeletal fluorosis and other toxic elements of volcanogenic origin appeared to be low. Instead, anthropogenic sources of toxic substances seem to have been much more commonplace, such as the use of mercury as a medicine and lead exposure resulting from regular contact with lead objects or infrastructure. In May of last summer, the Geldingadalur eruption was recorded as releasing over 6 tons of carbon dioxide, almost 3 tons of sulfur dioxide, and nearly 6 tons of hydrofluoric acid per day. But the health risks were generally limited to the area around the site and were altered daily by weather and wind conditions. Only on select days was the eruption site closed to tourists. During the eruption period, it was common to see people taking helicopter tours, cooking hot dogs on lava, edgy photo shoots, and even a wedding, with many people coming surprisingly close to the lava flows. Thus, while some eruptions in the recent past were clearly damaging and dangerous, not every eruption is the same, and many even make for the perfect tourist day trip. Surely we could say the same about volcanic eruptions in the past, though it is more difficult to speculate about how the society would have understood and responded to the situation. Relevant to the present day, this research suggests that it may be even more vital to reinforce socioeconomic circumstances, geopolitical conditions, and disaster mitigation protocols in regions with volcanic risk, rather than having any focus on the concerns over the severity of the immediate temporary effects resulting from volcanic eruptions. Thank you.